Okay, thank you very much. And thank you very much to all the organizers for putting together this amazing conference. Everything has been so smooth. And also thank you for the invitation. I'm very honored and happy to be here. So right, the title is Non-Diagonal Boundaries and AdS-CFT. So the theme of this talk is to use integrability to compute energies of string states. Because as you know from the AdS-CFT correspondence, these energies then are equal to conformal dimensions of corresponding operators in the dual gauge theory. In fact, I was happy to see this in one of the Gatta's films already. So we saw yesterday. So the outline of the talk is as follows. So first I'll begin with a review of the free closed string in AdS5 cross S5. So the reason for the review is that because then everything I say in this review will then be generalized to the case of the free open string with non-diagonal boundaries. So apologies to the experts for the review. They can sleep a little longer. And the novelty of this work, I think, is that for such problems with non-diagonal boundaries, there's no reference state. So the usual Bethe-Ansatz approach doesn't work. And then I'll try to explain how one can circumvent that problem. And this talk is based on the following 3 papers. The second one here is with a Chinese group. And the last one is with Zoltan, who's here. Okay, so let's begin with this review of the free closed string. So we all know, as a result of the effort of many people, most of whom are in this room, that if you work in the light cone gauge and take this decompactification limit, that this closed string can be regarded as an integrable scattering theory in one space and one time dimension. So it has a centrally extended SU2/2 squared symmetry. And it has 16 fundamental particles. We can denote them by alpha, alpha dot, where each of these indices runs from 1 to 4. And all of these particles have the same exact dispersion relation given here. And G is the coupling constant of the theory. And there's an exact S matrix. So it has a scalar factor. And then it has 2 copies of this SU2/2 S matrix. So each of them is 16 by 16. So altogether, this is a rather big matrix, 16 squared by 16 squared. So we have multi-particle states in this theory, which looks something like this. You have a ring, because we're looking at periodic boundary conditions, and you have m particles on that ring, and let's say its length is L. And they should obey the zero total momentum constraint. So PIs are the momenta of these particles. And so the energy of this state is, when the particles are widely separated, roughly just the energies of the individual particles given here. So if you want to know the energy, you need to know their momenta. And as I said before, by AdS-CFT, then this energy will be equal to the conformal dimensions of corresponding operators in the planar n=4 super Yang-Mills theory, and whose coupling constant related to this coupling G in this way. Okay, so then the main point is how to determine the momenta of these particles. So let's let's do a couple of warm-ups. First of all, suppose these particles on this ring are free. Then we know that because of the periodicity of the wave function, the momenta are quantized by this condition. So that's very easy. As a second warm-up, suppose the particles are not free and they have an S matrix, which is a phase. Then, as Zoli explained yesterday, if you take one particle and you take it around the ring, then every time it passes by one of them, it picks up an S matrix, and so then the quantization condition now becomes this. And this is the famous beta-Yang equation. As an example, suppose we consider the periodic spin-a-half Heisenberg chain, XXX chain. The Hamiltonian is here. So we have L sites, sigma n are the Pauli matrices at site n, and we're assuming this periodic boundary conditions. Then we know that over the ferromagnetic vacuum, there's excitations called magnons, and their scattering matrix is given by this formula, where the U is related to the P in this way. And if you now go ahead and you replace this S matrix into this equation, then you arrive at this one, which is just the famous beta equations.
I mean, since you're reviewing this as a concept, but already even here it's not just a phase.
Is not just?
It doesn't have to be a phase, right? It could be some complex number, and it will generically be.
Okay, I mean it's a number. Yeah. Okay. Yeah. Thank you. Complex number. Yeah. Okay. Good. Okay, and now for the last warm-up, suppose that the S matrix is not a number, but it's a matrix, bona fide matrix. Then the beta-Yang equation takes this form, looks similar, but now this quantity Sjk is the matrix corresponding to the scattering of these two particles of momenta Pj and Pk. So graphically, we can denote this matrix by this picture. So Bj goes all the way here, and then we have all these other momenta. And so what you're instructed to do is compute this large matrix and then compute the eigenvalues. And then they should satisfy this equation. Now we have a technical problem. How do we diagonalize this matrix? It's a large matrix. So there's an old trick, but very nice trick, which is to introduce something called an inhomogeneous transfer matrix. So I'll denote it here by little t. So we introduce one more variable, p. And the idea is you trace over in a new space called the auxiliary space, and denoted here by 0, of this product of S matrices. So each one has a foot in this auxiliary space 0, and then another foot in what's called the quantum spaces, of which there's m, as many as there are particles. And then we can denote it by, we can represent this by this picture. So the point is that now if we set this momentum p equal to one of the pj's, then somewhere along here, the two momenta will be equal. So we'll exactly at S0j. And typically, the S matrix for coincident momenta will just become a permutation operator, permutation matrix P0j, represented by this diagram. So then, if we go to this diagram, and now we put p is equal to pj, then exactly at pj, then the diagram opens up and looks like this because of this permutation. And since we also, in fact, have this periodic boundary conditions, in fact, this is really the diagram. And now if you just open this up, then you get to this picture here. So what I'm trying to say is that if you evaluate this in homogeneous transfer matrix at Pj, then you get exactly this matrix that we want to diagonalize up here. So then this problem then reduces to the problem of diagonalizing this transfer matrix. And then the good news is there's this very well-developed technology for spin chains to diagonalize subobjects. The basic point is that this S matrix will obey this Yang-Baxter equation that we've already seen. And therefore, the transfer matrix commutes for different values of this P, but with the same values of the inhomogeneities. And then, well, one more thing. If there is a reference state, then we can use algebraic beta ansatz, which I won't explain, then to determine the eigenvalues of this object. And so I say this is a big if because, as we'll see later, we don't always have this reference state, and then you can't use algebraic beta ansatz. So let's call the eigenvalues of this transfer matrix lambda. And then the beta Yang equation that I wrote before now becomes this. Right, this lambda here is this eigenvalues of this object we were trying to diagonalize. Okay, and that completes the warm-up. So now let's go back to the string. So remember our job was to compute the momenta of the particles on this ring so that we can compute their energy. And so now we see that the momenta of this multiparticle states are determined by this beta Yang equation, where this lambda is going to be the eigenvalues, which I'll denote by lambda 1, 1, of the fundamental transfer matrix constructed with this S matrix S, which I pointed out in the beginning of the talk. And I should say that this equation then is this famous Weisert-Stadler equation. And then, in principle, one can now solve these equations for the momenta. And then plugging into this formula, then we get the asymptotic energy for this particle state. But one can even go further. One can then also compute wrapping corrections. And let's just focus on the leading wrapping corrections for small weak coupling G. So from the work of Zoltan and Romuald, this correction, delta E, is given by this formula, where lambda here is the eigenvalues not of the fundamental transfer matrix, but in fact of all of them, because it's a sum here from A equals 1 to infinity, all of the higher transfer matrices corresponding to bound states of the fundamental particles. So the picture now is something like this, that for that transfer matrix, that instead of having just one loop running around corresponding to the fundamental particle, now we have A loops corresponding to this A particle bound state. So this is a transfer matrix whose eigenvalues we need here. And this correction corresponds to a Lucia correction where you have this A particle bound state and its antiparticle running around. So how to compute this, these higher transfer matrices? Well, there's several ways. One way is to use the fusion procedure. So this is something that was developed a long time ago for rational R matrices by Kulish, Reshetykhin, and Sklianin. And then recently it was upgraded to the case of this AdS-CFT type S matrices by Weisert, Deleu, and Nag. But there's a kind of a shortcut that one can take, still based on this fusion procedure, and that's to use generating functional. So for example, that appears in this work. of Gromov, Kozakov, and Viera. And I was reminded in Didina's talk yesterday that, of course, Nicholas before that. And in fact, you can even go before that. I think the earliest work I know is Kirillov and Reshetikhin in '87. They used it for the higher transfer matrices for the XXZ chain. So I'd like to review a little bit how that works. So as a warm-up, let's go back to this spin a half XXX chain, whose Hamiltonian I already showed you. So to build this Hamiltonian, we can start from some R matrices. So the R matrix corresponding to exactly to this Hamiltonian is the one here. So this times identity plus I times permutation. I put this shift here just for convenience, usually just see U. So I'll refer to this as the fundamental R matrix and denote it also by R11. And then I can denote it by this diagram. And then you can start to fuse. I won't explain exactly how, but it's not difficult. So roughly now you have two of these lines scattering with one of these. So this I'll denote by R21. So roughly speaking, instead of having two spin-a-half particles scattering, now you have two spin-a-halves coming together in the same way we add angular momentum, two spin-a-halves to get spin 1 and spin 0. But we project out the spin 0 and just keep the spin 1. And so now it's spin 1 scattering with spin-a-half. And that's this R matrix here. Oops. And you can keep going and get arbitrarily high spin. And then you can construct this transfer matrix. So taking the S fused with 1. So in other words, the auxiliary space is fused S times, but still the quantum space is still spin a half, so 1 to L. That's what this notation S1 tells us. And I'll denote this transfer matrix by T1 comma S for historical reasons. And then the picture is this picture here. So again, in the auxiliary space, we have this fused guy, and the quantum space just spin a half. And then because all of these R matrices satisfy the Yang-Baxter equation, one can show that all of these transfer matrices commute with each other. And then this Hamiltonian that I wrote here is given by the logarithmic derivative of the fundamental transfer matrix, this T11, evaluated at U equals I over 2. That's the point where the R matrix degenerates into a projector. Sorry, into a permutation matrix. And the fact that the Hamiltonian is contained in the transfer matrix and they all commute with each other shows us that this model is integrable. Okay, now how about the eigenvalues of all of these transfer matrices, which is what we want? Well, in this case, there is a reference state, and one can execute algebraic beta ansatz. And then it's an old story that the eigenvalues of this fundamental transfer matrix are given by this expression. So let's write it in a more compact form. So this coefficient here, I'll denote by phi. And then this product that appears in the denominators, both here and here, will denote by q, so this famous q function. And so then this long expression here for the eigenvalues takes on this simpler form. So we have this phi, we have q, and now q minus minus gives us this shift of minus I. So I've used this standard notation that putting plus shifts u by plus I over 2 and minus shifts by minus I over 2. And here I have two of them, so I shift twice. And likewise, the second term is phi bar, q plus plus over q. And if we multiply both sides by q, then you recognize this as the famous Baxter TQ equation. Okay, so that's the eigenvalues of the fundamental transfer matrix. And now using the fusion procedure, which again I won't describe, but it's kind of like just turning a crank, then we can get, say, the eigenvalues of the next one this lambda 1, 2. And if I introduce a further notation, I call the first term in the TQ equation A and the second term B, then instead of having 2 terms, now we have 3. And it's given by A plus A minus B plus B minus. And you can go on to get all the higher ones. And now comes the point that we can get all of these very cheaply from a generating functional. So to do that, we introduce this shift operator D, such that acting on any function of u, it'll shift it by minus I over 2. And so the generating functional producing all of these fused lambdas is given by this simple formula. So the way it works is that you just formally expand this guy. Here it is. And then you formally expand this guy. And then using the fact that D is a shift operator, you can just rearrange the right-hand side to get expanded in powers of D. So in this way, so D, and then D squared, and D cubed, and so on. And then what appears here is exactly A plus B, which you remember is the eigenvalue of the fundamental transfer matrix. What appears here is lambda 1, 2, eigenvalues of the fused one, and so on. Okay, end of review. So the point is that now in the string theory, one can, we have an expression for the eigenvalues, for the fundamental one, which we can get from algebraic beta ansatz. One can write a generating functional to give all the higher ones, and then we can plug back into the formula of Banach and Yannick, perform the integral, doing counter integration, and then get the wrapping correction. And in this way, we get the energy of the Konishi operator, 2-particle state with L equals 4, up to 4 loops, g to the 8. And then using more sophisticated techniques, this quantum spectral curve, which we heard about a few days ago, you can go at least as far as I know, up to 8 loops, so order g to the 16th, and probably even higher. On the gauge theory side, this corresponds to computing conformal dimensions of this operator. And up to 4 loops, it was found a long time ago. And then 5 loops more recently. But of course, everything matches. And that's a very nice story. Okay, so that completes the review of the closed string. And now I'd like to generalize all of this now to the open string. Okay, so now we'd like to consider m particles on an interval of length L. So now we have some boundary conditions on the left and right, and we have these m particles in between. And important thing for us is that we're going to insist on having integrable boundary conditions. So the problem remains integrable. So on the right boundary, we're going to put what's called a y equals 0 maximal giant graviton. So this corresponds to choosing a certain S3 D brane inside the S5. And then a particle then which will scatter from this right boundary will pick up a boundary S matrix factor, which we'll denote by this picture. So it comes with momentum p, it reflects with a momentum minus p. Now this boundary S matrix will have this form, as showed by Hoffman and Maldacena. So there's a scalar factor, and then there's 2 factors of R. And this R is just a diagonal 4x4 matrix given here, very simple. Therefore, the full boundary S matrix is 16 by 16, as it should, because we know that there's 16 types of fundamental particles. And notice that this R matrix has SU1/2 symmetry, because here these last 2 is just its identity on these last 2, so that gives us this SU2. But because of these factors of e to the I p over 2, we have only SU1 in this upper block. Now on the left boundary, we're going to put what's called the y theta equals 0 boundary condition. Okay, and what it is this D brane but rotated by an angle theta. So the boundary S matrix I'll call R theta. Again, it'll have the same scalar factor, R0, but now here are two copies of R theta P. And R theta P is just the R of P of Hofmann-Maldacena, but then rotated by an angle theta. So this O theta is just a rotation matrix in this upper 2x2 block. And again, here we have identity. And this angle can range from 0 to pi over 2. So notice that because of this, this rotation, that we kill this, this U1 symmetry that was existing in this upper 2x2 block. And so we're left with just an SU2 symmetry on this lower 2x2 block. So it's in this sense that we say that this is non-diagonal, because this R matrix, R theta, is not going to be diagonal. So it's not diagonal except for the 2 points when theta is equal to 0, when we're back to the YY problem, and that theta is equal to pi over 2. So this theta equals 0 case, the y equals 0 problem, on both ends, we looked at some years ago. And then the case of theta equals pi over 2 corresponds to a y bar on the left and a y on the right. We also looked at this some years ago. So what we're doing now is just trying to fill in between these two cases. Okay, so as in the case of the closed string, then if you want to compute the energies of these multiparticle states, we need to compute their momenta. And turns out that there is a boundary version of the beta-Yang equation, so we'll call it boundary beta-Yang, and it looks almost the same. The only difference now is that there's a factor of 2 here, because you should go from one end to the other, reflect again, so you move over twice the length of the interval. And also, what appears here is not the transfer matrix I showed you before, but a new object called the double row transfer matrix, which I'll explain in a few minutes. So lambda here, in the case of the string, will be lambda 1, 1, eigenvalues of the fundamental double row transfer matrix. And that's constructed with all the scattering elements here, the bulk S matrix and then the boundary S matrices that I already described. So again, we're faced with this technical question: how do we determine the eigenvalues of this object, lambda 1, 1, which sits here in this beta-Yang equation? Well, again, let's do a warm-up, and let's go back to the XXX spin a half chain, but now open. So now this is the Hamiltonian. So you'll recognize the bulk, so-called bulk terms. It's the same as in the case of the periodic chain. What's new is these terms here. So here we have at the first site, sigma 1, z, so in the z direction. But then this is the first site. But then the last site, we have sigma z with some coefficient, 1 over beta, and then sigma x with some other coefficient, c over beta. So these are the so-called boundary terms in the Hamiltonian. And these parameters here, alpha, beta, and c, are just some arbitrary parameters. They correspond physically to having some boundary magnetic fields. And I should emphasize that there's nothing pathological about this model. If I let alpha, beta, gamma, c be real, this is a perfectly Hermitian Hamiltonian, has a complete spectrum, everything is okay. But you'll notice that because if c, this coefficient here, is not 0, then because of this sigma x, there's no U1 symmetry. So then this has no continuous symmetries. And as I'll say in a minute, therefore we can't solve it by ordinary beta ansatz. But before I get to that point, let me argue that it's actually an integrable model. So to show you that it's integrable, then I should construct the transfer matrix. And the transfer matrix was, for this kind of open chain, was invented by Sklianin already a long time ago. And it's given by this expression here. So a little bit more complicated than for the closed chain. And it corresponds to this picture here. So let me take it one step at a time. So, so what appears here, this is K0 right, corresponding to this right boundary. Okay, and it's like it is a reflection matrix for this right boundary. So it corresponds to this picture. And this is what's going to give rise to the Hamiltonian, to this boundary term here, which is sigma 1z. It's diagonal. And so, so this boundary S matrix is also diagonal. And you notice that alpha appears inside here. So this is how the alpha ends up in the Hamiltonian. And in this boundary S matrix satisfies a boundary version of the Yang-Baxter equation, so called boundary Yang-Baxter equation. And here over on the left, we have this K0 left corresponding to reflections now from the left boundary. And here, this is non-diagonal. So it involves both the parameters beta and xi that you see in this boundary term. And this, in this non-diagonal boundary S matrix first appeared in the literature in these papers. Again, it's a solution of the boundary Yang-Baxter equation. Then this object here, T0, is just the usual monodromy matrix, product of all the R's with one leg on the auxiliary space and the other in the quantum space. And then this guy, T hat, is again product of R's, but now in the reverse order. So instead of 0L to R01, now it's 01 to R0L. And again, the R matrix here is just the one we saw before, is this identity plus permutation. Okay, so one can show that because all the ingredients in this transfer matrix, because they obey the various Yang-Baxter equations, then one can show that the transfer matrix, this double row guy, will commute for different values of spectral parameter. And the Hamiltonian here is given by just a derivative of this transfer matrix evaluated at I over 2. So that proves that this Hamiltonian is integrable. Now the question is how to compute its eigenvalues. Well, if this parameter xi were 0, then everything would be simple, because then the usual reference state, the spin up at every site, would be an eigenstate of the Hamiltonian and of the transfer matrix, and then we can just turn the crank of algebraic beta ansatz and find the eigenvalues. The problem is that when xi is not 0, so when the boundary terms are not diagonal, you don't have a U1 symmetry, then this reference state, this state is no longer a reference state. It's not an eigenstate of the transfer matrix, and then the usual beta ansatz doesn't work. And this was a long-standing problem, many years. No one knew what to do. And then there was a nice breakthrough a couple of years ago by this Chinese group. And they invented something they called the off-diagonal beta ansatz. And in hindsight, it's very simple. The idea is just to introduce an extra term, an inhomogeneous term, in this Baxter TQ equation. So this stuff here you already saw before in the periodic chain. So the new thing is this extra term. So the phi is not the same phi you saw before. It's given here. So notice it has dependence, as you would expect, on the boundary parameter. So there's an alpha, and there's a beta, and there's also a xi. And now the q is almost the same as the Q you had before, except it's doubled. There's a U minus Uj and now U plus Uj. And then the quantity I call delta here in this inhomogeneous term is written here.
But in terms of your very nice to read and logical exposition, that is really, it just falls from the sky right now.
I haven't explained it. I could say a few words, but then maybe...
I just wanted to agree with me that at this point, it's sort of, it's ad hoc.
It's ad hoc. I can say a few words briefly. So there's, what you can do is you can derive a functional equation for the transfer matrix. Okay, this again, there's a long history of this, goes under the name of analytical beta ansatz. And so one can formulate a closed functional equation for the transfer matrix, and then we imposed bootstrap conditions, crossing, stuff like this, unitarity, and asymptotic behavior. And if you do that, then you get this. So this delta, in fact, is fixed by insisting on the right asymptotic behavior. Putting such a term will not affect the functional equation, but without putting in this delta, you don't match the asymptotic behavior. So it more or less fixes it uniquely. So this was the initial approach, and since then there's been more work, and there's been some kind of modified algebraic beta ansatz. We can actually also recover this, actually recover not just the eigenvalues, but also the eigenvectors. So it's not ad hoc. Okay, and but thanks for the question. So, and the point is, if you don't do this, then you don't satisfy the asymptotic behavior, and then you don't get polynomial Q functions. So what's very nice here is that you have polynomial Q functions, so there's a beta ansatz. And notice that if we now dial C to 0, then this term becomes 1, and delta becomes 0, and we're back to the homogeneous TQ equations. Okay, so this is what I try to argue is appearing now in general. And now we can also get a generating functional because we're going to need this to compute wrapping corrections. And I claim that the right generating functional is this here. So if I call this first term as before A and this B, and now let's call this inhomogeneous term C, then the generating functional is given by this funny thing. And one can make an easy check. If I go for the diagonal case in which this delta drops out and this C is 0, then you realize that, that the thing inside the square brackets becomes this, right? And you realize that it can be factored into this expression. And that's just exactly what we had before, which is what you have for the open chain with diagonal boundary conditions. So I think you can believe it. And that concludes the warm-up. So now we go back to the string. So we can now construct the double row transfer matrix for a single copy of SU2/2. I already told you what the ingredients were. For the bulk, we have the Bizert S matrix, and for the boundaries, we have this Hoffman-Maldacena and then rotated one. And again, the double row transfer matrix looks just like the one I showed you for XXX, except now it's supertrace, and so on. And now we need a strategy to diagonalize this transfer matrix. And the strategy is to exploit this unbroken U1, right? Because I told you in the lower 2x2 block, we had SU2, so in fact a U1 symmetry. So we start with this reference state here, all spins down. And we can carry out the first level nested algebraic beta ansatz without any real problem. And that calculation is similar to the one for the Hubbard model. So that was done by Martins and Ramos for the periodic chain, and then by Guan for the open Hubbard model. So this is similar. Also, Galeas did a similar calculation for the open string with diagonal boundary conditions. And now, when you get to the second level, now you meet this problem with non-diagonal boundaries, and now you can use this off-diagonal beta-ansatz approach to diagonalize the second level transfer matrix. And this is the result you get. It looks a little bit complicated, but let me try to break it down. So, so the factors here, R plus and B plus, are appearing here, and they're just given by these factors. So similar to what you get in the case of the closed string, except it's doubled. This is in the notation of Gromov, Kazakov, and Viera. Then you have the Q functions appearing here. So this we call B1, R3, R1, B3, and Q2. And I've given them here. So the quantities Yj's and Wj's are the beta roots. And here, in both sets of Q functions, the number of roots are equal. We call little m, which can run from 0 up to big M, which is the number of magnons. And as I said, all of these quantities are doubled with respect to what happens in the closed chain. And then also appear some coefficients A and B given here. What's most important is this last guy here. So this is this so-called inhomogeneous term, which we needed because of this non-diagonal boundary conditions. So that's this inhomogeneous term. And if you dial theta to 0, then you see that this term drops out. So yeah. So because of this, because of the appearance of this inhomogeneous terms, and the beta equations will get modified. You don't have to look too carefully at them. The most important point is, again, one beta equation is not modified, and then this other one here gets an extra term because of this theta. And as a check, we obtained all 4 to the m eigenvalues of the transfer matrix numerically for m is equal to 1 and 2. So we checked the completeness, so we have confidence in this result. And then also this generating functional I showed you before for the XXX, same trick can now be applied here to generate all the fused all the eigenvalues of all the fused transfer matrices too. And so now with this, we can now try to compute the wrapping corrections at weak coupling. So there's a similar formula as before. Main difference is, again, there's this factor of 2 here, and now the object here is the eigenvalues of the fused double row transfer matrix. And then we can get these now using this generating functional that I just mentioned. And I'll spare you the details, but one can now compute the energy and also these wrapping corrections for one particle states as functions of this twist angle theta. So the picture is here. We have just one particle, P1. We have these 2 boundaries. So for example, in the case of length 2, then this P1 as a function of theta can have these values. Okay, so there's different states, so different momenta. And then we went ahead and computed the energy corrections as functions in g and theta up to order g to the 12th. So if you want the explicit results, they fill up like half a page. You can look in the paper. And what's nice is that there's exact agreement with the previous results for theta is equal to 0 and pi over 2. So there's still many questions. So one is, can we compare this with gauge theory? So we need someone very strong to do the gauge theory calculation. Also, it would be interesting to see whether this could be obtained using the quantum spectral curve, and then you could presumably go much further than leading wrapping order. So to conclude, I've tried to argue that integrable non-diagonal boundaries can now be solved. The key idea is adding this inhomogeneous term to the TQ equation, and it can be applied to the spectral problem in AdS-CFT. And then we used this to compute parameter-dependent wrapping corrections. Okay, thank you for your attention.
Thank you very much, Rafael, for that very nice talk. Are there further questions? Yes, what's the gauge theory correspondence of your open stream?
Okay, thank you for these boundaries.
Yes,
Yeah, okay.
And also, why is there some physical understanding why this specific boundary condition is integrable? Because generic boundary conditions typically present integrability.
Okay, so let me address the first question first. Thank you for the question. So I have a little bit here more. So say a little bit more about this y theta y system. So there's kind of Gauss's law constraint, which tells that, I learned this from Nadav, that a compact D-brane cannot support a single open string. So we need at least two open strings with opposite orientations. So kind of like this picture here. But in the planar limit, the strings do not interact. So what I told you here was focusing on just one string was justified. We can consider the spectral problem independently for each open string. So if you want the dual gauge theory operators, you really need a dual gauge theory operator corresponding to this picture. And then it's a little bit complicated, but here it is. So y hat is a linear combination of the fields y, x, x bar, and y bar. And in principle, you can make two rotations on the two SU2/2s, so theta 1 and theta 2. And in what I discussed, I kept the two angles equal, so theta 1 equals theta 2 equals theta. So that's the subject y hat. So what you see here this is just a shorthand notation for two epsilon tensors. So epsilon A1 to AN times epsilon B1 to Bn. So this is the n of SUN, and n is going to infinity. And you contract the lower indices of the y's with the upper indices of these epsilons. And you notice you contract all but one. So I have A1 up to AN minus 1. And then for the b's, I contract these lower indices of the epsilon tensor with the upper indices of the y's. Again, all but one. And then similarly for the y hats, I have two epsilon tensors, D1 to Dn. I contract all but one, and the same thing here. And finally, the last indices, the DNAN and BNCN, are here. And those are kind of words. And these words are the ones that contain the information about what excitations you have on the string. So you need to compute the anomalous dimensions of these operators at large n. And so this is the problem that needs to be done. Yeah, and these are called determinant-like operators, and they've been around for a long time. Second question was about integrable boundary conditions. So y equals 0 doesn't exhaust. There's others, like z is equal to 0, and there's others. They haven't been classified, but that's true even in the case of the bulk. People haven't classified the solutions of the bulk Yang-Baxter equations. So, and I don't have any physical intuition what makes one integrable and one not. It's a good question.
Time for another question? I think I have a question myself. These off-diagonal differential technique can be used also for theories like XYZ speed chain difference.
Okay, so XYZ periodic or open?
Just periodic.
Yeah, so for periodic, you're right, you don't have U1 symmetry, but it turns out that you don't need to do this, at least for even number of sites. So there's this very nice work of Baxter, and then it was reformulated by Fadea Takhtajan, where the idea is that you make, at each site, you make this local gauge transformation, so you have sort of a local vacuum, and then you can implement algebraic beta ansatz for that, and you can do that. For odd n, I think you cannot do that, and then you need this kind of inhomogeneous term. And if you say, okay, try to do the same thing for the open chain non-diagonal, so that's also been considered by a subset of this Chinese group a long time ago, and what happens is that you still can't solve it for generic boundary parameters. You require that the left and right boundary parameters satisfy some constraint. So if the constraint is satisfied, then you can do this Baxter trick and not introduce this extra term. But if you have generic boundary terms on the left and right, then even this is not enough. And as far as I know, the only way to do it is using this inhomogeneous.
What's quite interesting in the context of AdS-CFT is that in AdS2-CFT1, there are X, Y, Z like R matrices that appear for the closed range vector.
Oh, right.
That we can just discuss.
Okay, I'd like to hear about that.